Hello guys, welcome to this new session. Let's continue developing our end language. In this section we will do something unusual. We will optimize our end interpreter. So as you see here, my title is benchmarks, profiling, a hotspot and optimization. So the benchmark is a test reference used to measure performance of something, and we need to measure the performance of our end interpreter. So we need to prepare a benchmark script that we interpreted by the end interpreter, as this benchmark script is like a script that make a load on the interpreter or a stress on the interpreter, and then we need to use a profiler. It's just a tools that profile the interpreter after the benchmark, and it profiles it by showing us how much memory allocation or function calls or execution times, and then we identify the hotspots. So the hotspots is the spots in our end interpreter that take so much memory, or it allocates so much memories, or it has many calls and so on. And after that, the third phase is when we analyze these hotspots after profiling, we need to come with some optimization. So that's it. We have benchmark as a script that traces our interpreter, and we have our profiler that profile that interpreter, and then we need to determine the hotspots, and then we need to come up with a solution to optimize these hotspots. So let's jump right to the code, and I've prepared a benchmark. So you see a directory called benchmark, and I will change the directory to it, and I will just print our benchmark script. And as you see, we have a declaration of a class cinema, and with a constructor that assign to these properties ACD number 1, and then we have 6 functions. The first function is like types of films: action, we return this.a; for comedy, for drama, for romance, and so on. So then we instantiate a cinema object, and then we initialize a variable sum, and then we have a starting clock that remember in seconds the starting clock, and then we have a loop that loop over 100 million times, and we sum up these values 100 million times, and then we print the start the clock now minus the start clock, and then we have how much time this took to give us the result. As you see, this is a benchmark. It will stress our interpreter to determine the hotspots. Why is that? Because we have the loop will turn 100 million times, and also in this 100 million times we will use hash tables to get the values, and you see. So we have 100 million times calls, and this is a benchmark. It's a reference that will stress our interpreter to measure the performance of our language. So let's run that on that benchmark. Let's run our interpreter on that benchmark and see how much time it took to finish. So let's do it, and I will print that benchmark. So let's first of all check the common.h. Okay, and I need to deactivate these macros of debugging. So let's rebuild the project. Okay, all is fine. So before running our benchmark to stress our interpreter and then run our profiler to see and to detect what are the hotspots, we need to change our make file and add a flag P. So this flag P will generate a file, the file that we need to profile, and P is stand for profiling. So let's rebuild our project. And okay, everything is good. So I will cut my benchmark and then I will execute that script, that benchmark, and we will wait for the response. It will take some time. So as you see, our script or our benchmark, it takes this much time and it's too much. So I will list my directory and see that we have a new file that is generated. It's gmon.out. It's generated because we did the flag P, and from now I will execute our profiler to see what's the result of the profile, and then I will detect the hotspots, and then I will go to optimize this hotspot. So what I need to do is to use a tool called GNU profile. So on the end interpreter, and the output file is gmon.out, and I will redirect the result to a file. I will call it old profiling.txt. So why I name it that? Because when I will do optimization, so I will execute the same command and I will redirect the results to a new profiling to compare the old version with the new version. So let's do it. So I will create that and I will go to old profiling. Okay, I will cut it. And then I will go to the top. You see that's all the profile and all the functions that are executed when we execute the benchmark. And here you will see, and if you analyze, you will see that we have this function, find entry, this much calls it takes, and it takes 29 or 30% of the execution time. So in this function, I will take it as a hotspot. So let's see the peak function. The peak function, it has more calls than find entry, but it takes just 6% of the execution time. But the find entry, it takes 30% of the execution time. So here I will go to find entry. So our hotspot is the function find entry. So I will go and see if I can analyze it and see what are really the issue, and I will solve that by optimizing that. So let's go to table.c on the function find entry. So guys, after analyzing and see, we detect that this is the hotspot, but the real instruction that takes much time is this instruction due to the operation module. So there is a optimization for that. We will use the new one. So just forget I used the unsigned 32 instead of index, it's not a problem. So I will replace it by doing one operation and the bitwise operation and with the capacity -1. You can go and search on Google. This is equivalent to this. The same result in this is the same result on this using this modulo operation, and here we will use a AND operation to get the same result. And AND operation, it's an operation faster than modulo operation, so this, it will help us optimize this hotspot that we figure out. So we can go further and remove this operation -1, but we need to change a lot of things to get the capacity -1. So we can replace that with that, and this is the optimization. But you should keep in mind that the capacity that we need to pass to this function is the whole capacity -1. So to do that, I will go to capacity and initialize it with -1, and I will go to also here in modulo, I will replace it by AND. So in the allocation, I will allocate capacity +1, and I will go from to the capacity because okay, also here for this 4, and let's go, and here in the grow capacity, this is the capacity, and I will cut that. I will paste it here. So the capacity, it will grow the capacity. Will grow the capacity, but we need to do something. Remember, our capacity starts from -1 at the first time. So what I need to do is to start from at each time I will start from the capacity +1. So in the first sum we have -1, so I will pass to grow capacity 0. So this is the normal thing, and then I will subtract 1 from the capacity. So guys, remember, the whole thing is to pass to find entry the capacity, but is subtracted by 1. So what I did is to grow the capacity and subtract 1. So then I will pass it to adjust capacity, and it will set the table capacity to the new capacity, but it's subtracted by 1. And when I will turn the loops and that, so I should go to the table capacity to exact. So let's give an example. So let's say that this it returns 7, and 7 it will be stored here. It should be stored here, but 7 I pass 7 to adjust capacity by I allocate 8. So that's the whole idea. And let's also update that. I will add one. Okay, let's choose for loops, and for loops I will go from this and until the capacity. So also I will just update this things, it's end operation, and also I just change that type to int 32. So here also I will change that to end. So that's it. This is the whole optimization, and you can go and search for what's the proof of this operation, why these two things are equivalent. The model operation is equivalent to this one, but the capacity is subtracted by 1. You can go and search for the proof. So there is many proofs out there, and you will understand that. Okay, I will make okay, everything is good, I guess. So that's it. So I will go to the memory, our memory.h header. So because here I pass operation with I pass a value with an arithmetic operation, so I will go to memory.h and add parentheses around this, because we need to avoid that because we need that this operation it has the priority before doing a multiplication. And also here alt capacity, and also here, and also here, we just do parentheses around that to avoid any arithmetic issue. So let's clear that and let's rebuild the project. So everything is good. So let's run. So let's remove that, the previous Gmon, and let's run our interpreter on the same benchmark. Bench content, and we will wait for the result. So as you see guys, the result is this. So let's go and run the same command on that, but I will do new profiling, and let's open the old profiling, and let's see the new profiling. So as you see here, in the previous one, the hotspot is find entry and it takes 29% of the time, the execution time, but here as you see it takes only 17% of the time. So that's much more from the previous implementation of hash table. So guys, we stress our interpreter and we profile that and determine the hotspots, and after analysis we get some optimization. So in our example here guys, we did a benchmark for hash tables and we detect a hotspot on the find entry, and we see is that it takes 30% of the execution time, but after the optimization, the same function, it takes only 17% of the execution time. So it's a much better implementation of hash table, and our end language now, it's much faster than the old version. So see you guys in other session, and we will do another optimization so our end language it gets much stronger than the previous versions. So see you guys in other session. We did I think good. So we profile our interpreter and we detected hotspots and we did optimization. So see you guys in other session.